Hello everyone. In this video I'll be discussing about a practical implementation that we have built to visualize synchronization in dynamical systems. Before we proceed further, I would like to discuss a few things about synchronization itself. The universe that we live in is filled with disorder. The second law of thermodynamics says that we are on a trail of ever increasing entropy. The nature around us is highly nonlinear in nature. The nonlinear system exhibits a lot of features such as multi-stability, fractal geometry, and most prominently, chaos. Chaotic systems are again ranging from are all around us, ranging from cosmic inflation all the way to human brain. Chaotic systems often give rise to emergent phenomena. One such fascinating phenomena is synchronization. Now, what is synchronization? Synchronization can be defined as the correlation between the elements of a dynamical system. So, if the correlations are complete or they all exhibit the same behavior, they all work in unison, it's called a complete synchronization. Or if there exists a functional relationship between these variables, then we can call it as a generalized synchronization. Now, the model that we have built is inspired from fireflies that flash in unison. So, some species around the world, a few species around the world, actually exhibit unison flashing patterns to attract their mates. Our model is basically inspired from these flashing fireflies.
The Kuromoto model is an established mathematical model that describes synchronization in coupled systems. This was proposed by a Japanese physicist, Yoshiki Kuromoto. To understand this model, let's consider n coupled oscillators. Let the phase of an ith oscillator be theta I and the intrinsic frequency be omega. Let's define a coupling constant k that describes the strength of correlation between these oscillations. Now we can write a functional relationship between this theta I and the theta adjacent theta j, such that theta I dot is equal to omega I plus some k times the sum of sines of theta I minus theta j. The sinusoidal term, which includes sine theta I, theta j minus theta I, describes the relation between two oscillators. Also, the k term describes the strength of correlation, as I explained before. Now, what happens if we increase k from 0 and to a value? So, as we increase k, what happens is the strength of synchronization keeps increasing. At before, when the k is 0, there is no synchrony. The system is randomly oriented, and as you can see in the animation, the system is you can see the phase oscillators are randomly moving around the circle. But as I increase k, after a point, the sudden phase transition occurs, and after this phase transition, always the system tends to synchronize, and it always reaches to a synchronized state. Now, in our model also, we observe the same thing. As we increase k values at k equal to 0, we don't observe anything, and after a critical value of k is reached, we see a sudden sharp synchronization starts to occur, and after that the system synchronizes faster and faster as I increase k.
Now, before explaining what our model is, I would like to tell what is the base, what have we built the model upon. So the heart of the project is an Arduino Uno, and the Arduino Uno runs an Euler scheme that solves a differential equation, the Kuromoto differential equation inside, and it produces outputs, and these outputs are given to a set of LEDs. In our model, we have 64 LEDs arranged in groups of 8. Now, the feature of our model is that these 8 clumps or 8 groups we term it as nodes. So these 8 nodes contain 8 LEDs or 8 individual oscillators. So all these individual oscillators are independent, but in a clump, to see this more clearly, what we have done is each node is controlled separately by a single Arduino pin, and all of these LEDs are individually addressable. So what happens is our system synchronizes every group or every node synchronizes first, and all of these nodes, because they all are converging to a driving frequency, all of them synchronizes into a single as a single system. So they all flash in unison by the end of the differential scheme. In the end, I would like to emphasize that this project can be a very good tool to visualize synchronization as an emergent phenomena. All the detailed resources, including the circuit diagram as well as the Arduino code, is included in a GitHub repository, and the link is given in the video description. I hope you all gained some insight into what synchronization is and how to implement it on a practical level with this video. I would like to end my presentation here, and thanks a lot for watching.